Hi everyone, welcome back. So in this problem we are dealing with a circuit that has 3 diodes. They tell us that each diode has a cut-in voltage of 0.65 volts. Let's immediately start writing out our information. The question asks, what does R have to be for the current in the output diode to be half of the current in the input line? That's an interesting constraint. Let's write that out mathematically. They give us a current as it relates to another current. When dealing with purely current, we typically need to do a KCL or a similar analysis. So let's start with that. I'm going to do a KCL at the node that branches line 1 into lines 2 and 3. We'll call it node N. Right in the beginning, we can substitute the first constraint into the KCL. Perfect. Now we know that I1 is related to I3, which only passes through one resistor. It can't get simpler than that. We just have to use Ohm's law on the 1 ohm and we'll have I1 right after. We'll need the voltage on the 1 ohm. It's in parallel with the output diode and as such shares the voltage with it. So, yay! We just have to know the voltage on the diode. Time for a quick diode run-through. Okay, for diodes, the positive end is on the triangle and the negative is on the slash. I think the slash looks like a negative, so that makes it easy for me. Remember that cut-in voltage they mentioned in the beginning? That's just a technical way of saying that the diode needs 0.65 volts to turn on. I just call it the turn-on voltage when I'm lecturing to my students. Anyway, a diode is kind of like a switch that only closes once it gets its turn-on voltage. Once it activates, it doesn't take any more volts. I repeat. Once on, a diode maintains the turn-on voltage, no matter how big the source is. If the diode receives anything less than the turn-on voltage, then it's, well, off. So when a diode is on, it lets current pass freely through it, basically acting like a short circuit. Except instead of it being 0 volts, it's a short with the turn-on voltage holding it still. You can redraw an active diode as a short if you want, so long as you label the turn-on voltage across it. When a diode is off, it doesn't allow any current to pass. It acts like an open circuit, and you'll have to calculate the voltage that it stores with some more circuit analysis. All you know is that the voltage will be less than the turn-on voltage. And just like that, bam, you are now equipped to deal with about 80% of diode problems. Congratulations on leveling up to an electronics guru. Now, back to the 1 ohm resistor. The circuit has 5 volts powering it. We are going to assume that's more than enough to turn all 3 diodes on. The voltage on the diode and the 1 ohm is the turn-on voltage because they are in parallel. 0.65 volts and the current, I3, is 0.65 amps. Yes guys, once you get it, it's that easy. God, I love that ad. The beat drop just takes you, back to the problem. Far found I3, so that we could plug it back into I1. Solving engineering problems is like a mission that involves side quests. I1 ends up being 1.3 amps. All of that solved from just the opening constraint. Now how do we use that to find R? Remember, that's the main quest. I1 passes through R. Ohm's law says that if you know the voltage and current on a resistor, you can solve for the resistance. That's our ticket. We need the voltage, so let's try a quick KVL loop involving R and every voltage that we know. In this loop, there is just R and the 3 diodes. But the great thing is that we assume all of the diodes are on and use up 0.65 volts each. A simple KVL, really. Solving for V, we get 3.05 volts. Now with that, V equals IR is complete. R ends up solving out to be 2.35 ohms, and we're done. Nice work, everyone!